So what I'm going to do is just go over quickly what we did last, when was it, Monday, right? And then do some examples so that to help you with the homework. And then you do the lab this Friday, so we are sort of done with topic and we go to the next one where we need all this stuff. So the Fourier series result is that for periodic signals, this is a periodic signal. So the definition of periodic signal is for any t, any small t, if you shift it by some amount, capital T, the signal is the same. So that capital T is the period in this picture. So this is the period of the signal. So Fourier's theorem is it has a periodic power series representation like this. So where this omega naught is 2 pi over t. This is called a fundamental frequency because after all this is complex sinusoid, sine and cosines. So this is a complex sinusoid at frequency k omega naught. K is this index, and here Ck is the amplitude. Remember, this is something like cos k omega naught t plus j sine k omega naught t. Since sine omega naught t or cos omega naught t is a waveform with the frequency omega naught, here the frequency is k omega 0. You have an in-phase component and you have a quadrature phase component, or you can call it a complex sinusoid. And so the Ck must be its amplitude. In general, that is also complex. And Ck is given by, we went through all this, 0 to t, ft e raised to minus jk omega naught t dt. Notice that some definitions you may use a minus here, then this will be plus, that's all. So this is in general could be complex because this can be written as, if you substitute for this is integral ft cos k omega naught t minus j 1 over t integral 0 to t ft sine k omega naught t. So if you call this to be ak, then minus j, this is bk. So ak's and b, so in any case you see that the ck's could be complex. So ck turns out to be ak minus j bk. So that's our notation. So ak is 1 over t integral 0 to t ft cos k omega naught t dt, and bk is 1 over t integral 0 to t ft sine k omega naught. So if ft is real, so ft could be complex in general, but if ft is real, you notice that ak is real because this is real, and bk's are real. So that's if this is real, then we can use this representation. So if ft is real, then ft can be written as sigma ak cos k omega naught t plus sigma bk sine k omega naught t. All this we did last time. K goes from minus infinity to plus infinity. So in general, if for a real signal, you just find the AKs and BKs. Now I also told last time without proof that you can actually, the CK, here I wrote it, the definition was from 0 to t over any one period, but it can be, the integration can be over any interval so long as it covers a period. In other words, you can start some t naught, you just have to end up at t naught plus t. So to show that, let me define dk to be integral from or I will see why. Let me write dn this way. So what is the difference between ck? Look at this. Ck was defined from 0 to t, whereas here we are defining it from some t naught to t naught plus t. Still it is shifted by t. So I'm going to show that this dn is the same as cn, which will mean that in some problems, if you feel like doing, if it is easier to the integration over some other duration, you can do it. So let me substitute for ft from here. So this now reads sigma, ft is what? Sigma ck. So ck I'm going to put it here. Then e raised to, I'm using this expression, j right? I just I put this expression there, I coupled it together, so you get that expression. K goes from minus infinity to plus infinity. But remember, we have done this integration of this. Again, call this, so what's the one more time, what's the integral of, or before that?
Why do we not include 1 over t?
Yeah, I mean, one over t is there, right? Otherwise, we'll get t times that. But thank you, that's good. So, right. So I defined dn to be this way. I'm going to show that dn is the same as cn. So to make further progress, let me define a new variable t equal to t naught. Or x equal to t minus t naught, so that t is x plus t naught. So notice here dt, t is the variable. So if you take the derivative of this, you get this is a constant, dx is dt. So this integral becomes 1 over t summation over k ck. Then you have integral e raised to j k minus n. Then you have omega naught. So instead of t, I'm going to put x plus t naught and dx. Okay, now how about the limits? Look at here. When t is t naught, x is 0. And when t is t naught plus t, this is t. So I just wanted to shift it. And the integration is only with respect to x. So I'm going to pull out a constant, 1 over t summation ck. I don't know whether you have looked at it, but this proof is there in my notes, but I'll just do it here quickly. And I can pull out the terms involving t naught outside. So this now becomes and we have seen this integral before. So if you want, for the time being, call this to be m. You remember this m only takes m is 0, one value, m not equal to 0. So anybody, what is the value of this in this expression? Anyone? Remember, we did this.
If k is equal to n, otherwise.
Yeah, just call it in terms of m first.
So m equals 0, means that the whole thing is 1.
All right, so m equal to 0, this whole thing is 1. M is not equal to 0? 0. So when m will be 0 when k is n. So do you see this? I don't have to, I can redo it. This whole integral is 1 when n is k, and it is equal to 0 when n is not equal to k, or k equal to n. Same thing, k not equal to n. So here k is the running variable. So as k goes between all values, k will hit n also. When k hits n, this is 1. All other values, it will be 0. So this will be equal to? Because when k is n, this term also gives you 0. I'm sorry, the exponent is 0, e raised to something is 1. What did you say? Cn, right. So I showed that dn is equal to Cn, which means that you can do the integration over any duration. It's a useful thing, as we are going to see soon. Okay, so that was a side result. So let me take off this and save this space. So basic thing is you can integrate to find out Ck, you can integrate over any duration. Then sometimes the signals will have symmetry and we want to exploit that. So if there is no symmetry, you just find out the A case and B case using this expression. So if especially we did Ft is real even. Remember, even signal means it's like this. And Ft is odd, real and odd. So that means the signal is like this, or like this, etc. Remember, it's a periodic signal, so it goes on forever. So these are two different examples here.
If it's periodic, why did you draw the line?
Yeah, what I meant was, so when I meant periodic, this is what within a period.
Oh, okay.
So that would mean that, yeah, it's a good question, so it will go like this. Same thing here. So I just showed what is within a period. Then this will be in mathematically it means f of minus t at some minus t is the same as plus value. Whereas here, see, minus t, it's the negative of that. This is t minus t. So f of minus t is minus fft. We went through this last week, but I'll just quickly do this and then do a few problems. Then I'll briefly talk about convergence and so on. And so if you look at AK here, AK is 1 over T. So you see, whatever we just discussed, I'm going to use this. Because it is even, I want to exploit that. I'm going to do, instead of doing the integration from 0 to T, I'm going to do over a symmetric duration. Nothing is lost because it's exact. We already showed you, right? So Ft cos k omega naught T dt. And if this is even, the product is even, right? And the even function integrated over a symmetric region is the same as twice over half of it. So you also have this simplification, 2 over T integral 0 to T by 2 Ft cos and if you look at Bk, it will be 1 over T integral minus T by 2 to T by 2 Ft sine k omega naught. So what is this value? Anybody? This is even, this is odd. So product is odd. Odd is like this. So if you integrate an odd function over a entire period, it will be 0, right? So BKs are 0 here. So to continue, so that means the Ft here Look at here, all the bk's are 0. So if the function is real, you only have the ak term. So I'm going to pull out the a0. So this is simply sigma ak cos k omega naught t. So as I told you last time, we can pull this into 3 sets of terms. ak cos k omega naught t plus sigma. So this is k equal to 1 through infinity. Here k minus 1, minus 2, etc. up to minus infinity. Also ak cos k omega naught t. So here the values are 1, 2, 3, etc. So here minus 1, minus 2, minus 3. So if I change a variable k to minus m will take the values 1, 2, 3, etc. So instead of k, I can put minus m. So this will become a of minus k, right? Or a of minus m. This will become minus. So you do that mentally. Instead of changing the k to m, I'm simply going to change k to minus k. If I change k to minus k, I put a minus here, I put a minus here, I also put a minus here. That way all these minuses, this will become minus k equal to minus 1, 2, 3, etc. That's the same as saying k is 1, 2, 3 up to infinity, which is same as this. But we know cos of minus theta is cos theta. So this is cos k omega naught t. Now finally look at a of minus k. You can look at from here. If you put minus k here, it becomes minus here. But cos of minus k is cos. So a of minus k is also ak. Do you see it? Because put minus k here. There is no k here. K only comes here. So that becomes cos of minus k omega naught t. Cos minus theta is cos theta. So that's the same as cos plus k omega naught t. So this also tells you a of minus k is ak. Since we are here, let's look at b of minus k. If you put b of minus k in any expression, forget about this. K, this sine of minus theta, minus k omega naught, sine of minus theta is minus sine theta. So this will also tell you that b of minus k is, we will need this minus of bk. But it doesn't matter here because you only have ak's. So bottom line is this expression is exactly the same as this. So we can write this as a naught plus 2 times sigma ak. So that's for real and even signals. And if ft is real and odd, so first of all ak, which is 2 over t minus t by 2 to t by 2, ft, did we do this already? Okay, ft cos k omega naught t dt. What's the value of this? This is odd. This is even. Odd multiplied by even is odd. Over a symmetric duration is 0. So all the bk's are 0. I'm sorry, all the ak's are 0. So you only end up with the bk's. But look at here, for any function, it doesn't matter what the symmetry is. Look at here. What's the value of b0? Anybody?
0.
Right, b0 is 0 because if you put k equal to 0, that's gone, right? So ft, you only have the bk terms and b0 is 0. So you have k equal to 1 through infinity bk sine k omega naught t plus k equal to minus 1 through minus infinity bk sine k omega naught t. Right? So same thing, you replace k by minus k. So I'm going to put minus here, minus here, minus here. But minus k equal to minus 1, 2, 3 is the same as k equal to 1, 2, 3, etc. So we got the index same as this. B of minus k somewhere we wrote here, minus of bk. So this is minus bk. Sine of minus theta is minus sine theta. Minus minus will become twice. So this term is exactly the same as this. So we get this summary 2 sigma bk sine bk not t dt. So k goes from 1 through infinity. So that's the sort of summary. So we have AK here, BK here. Keep in mind, from problem to problem, you can change the limits as you find it convenient. So let me do some examples. So let me start with this problem. So what's the period here? Anybody? So what is omega naught?
2 pi over t.
What is t? Yeah, so t here, this is t, right? You can see from the picture. Or this is t, whatever. So t is 2 pi. Consequently, omega naught is 2 pi over. And what sorts of symmetry do you have? Also, we are already on to that one. So, right. So ft is of this form, sigma bk sine k omega naught t, k equal to 1 through infinity. So you only need to find out bk. Bk is 2 over, what is it? 1 over t, right? What is this now? 2bk, right? B is 1 over t integral from. So here you see, to exploit the symmetry, do it from here to here. You can do it from here to here also, but then it is a shifted symmetry. So minus t by 2, t by t to 2, ft sine k omega naught t. I can do one, let me just do one more. See, if this is real and even, look at here. Maybe did we, yeah, we wrote it here, 0 to t. So that's also true here. What will be bk? B0 is always 0. If this is odd, pay attention here. If this is odd, this is always odd. So odd multiplied by odd is? Even. An even function integrated over double is the same. Symmetric region is the same as 2 times integral from. So here in this case, so at is 0, ak is 0, and bk will be, you have this simplified formula. Bk is given by, you can use that formula, or 2 over t integral 0 to t by 2 ft sine k omega naught t dt. Look at here. So it may be easier to do the integration that way. So we can, you don't have to remember any of this. You can see here also. This is odd. This is odd. Odd, odd is even. Integrated is the same as 2 over t integral from 0 to t by 2. T is how much? In this case, t is Yeah, so this will be pi. And ft is, I'll write one more line, ft sine k omega. What is the value of ft? 1. So you can write another line, so I'm just, so this is, you have to do this integration. So what's the integral of sine? Negative cosine k omega naught t over, there is a constant also, 0 to pi. Constant is 2 over t with a minus sign. T omega naught is t multiplied by omega naught. What do you get? T multiplied by omega naught. 2 pi. T multiplied by omega 0. See here, t multiplied by omega 0. I can replace it by 2 pi. 2 cancels, so you get 1 over pi, right? So first of all, omega naught is 1, right? So I don't need omega naught. And cos 0 is 1, right? So this you can write as 1 minus cos k pi divided by, what did I say? Pi k. Everybody agrees with this? See how I did this simply? Because lower limit, cos 0, that's 1, with a minus sign, so that comes here first. Upper limit is you put pi here, so that becomes, why did I remove omega naught? Because omega naught is 1. And I don't have to write, t is actually 2 pi. Anyway, t multiplied by omega naught is 1, t is 2 pi, 2 cancel, so I have a pi here. What is the value of cos k pi? Anybody? When k is, remember, these values, you don't have to worry about 0. You only have to worry about k equal to 1, 2, 3, etc. When k is 1, cos pi is minus 1. So 1 minus minus 1 will give you, what will be the numerator? 2. When k is 2,
1 minus 1.
that is what? 0. Okay, is 3? 2. K is 4? 0. So you see the pattern, right? So this I can write it as yes. So this sort of stuff you need to look at the problem. Each problem you have to do. So you just play with a few numbers. K equal to 1, as I said. Minus 1, 1 minus minus 1 is 2. Denominator stays whatever is the k. When k is 2, 1 minus 1, 0. K is 4 pi, that's 1. So 1 minus 1. So 2, 4, 6, all even numbers, the whole thing is 0. Odd numbers, it is 2 over 1 over pi k. So this will, for example, so this problem will come out to be 2 over pi, then what is it, sine t minus plus sine 3t by 3 plus sine 5t by 5. So that's the way, that's what I expect. That's the Fourier series expansion of this square wave. We did another shifted square wave with a different kind of shifted square wave, so that it had even symmetry, and that we did last time, so I'm not going to repeat it, right?
What would be 4 by pi? 4 by pi?
Yeah, 4 by pi also, right?
On the outside, you're multiplying by 2 by pi, 1 by pi.
What about it? 2 by pi is common.
But you multiply it by FP is 2 before.
Okay, so this is bk, so this should be 4 by pi. Is that what you're saying?
Yeah.
Okay, so the general term is, for example, sine kt over k, but all with the plus signs, plus etc. So this is an infinite series. So
It should be 5,
Yeah,
not
only
4.
in the odd ones.
what?
It should be 5, not 4. Only odd numbers.
So sine, it should be sine 80.
Not sine 4.
No, look at here. When k is even, this is 0.
Yes.
Sine 5.
Your third term is,
Yes, so term is 5. So why were you trying to confuse me? Or you were trying to say here? Okay.
Also, it should be 2, not 4, because you're dividing by t, which is 2 pi. So it's 4.
Hang on. There is a 2 here. That's what he was trying to say. This is 2 over pi k. 2 multiplied by 2, 4. That's what this. Okay, so we are done with this. Let me move on to a slightly so I'll save this and erase this. Maybe do another a classic problem, another odd one, which is a sawtooth waveform. So let me. So the result turned out to be omega naught is 1, so this is good. What was it? 4 over pi summation k equal to. For odd values. So the way we are going to write odd values is so think of put k as 2m plus 1 and divide by 2m plus 1. Remember, k goes from 1, 2, 3, etc. So m will go from 0 through infinity. Because when m is 0, you get k equal to 1. When m is 2, you get k equal to 3, etc. So you can write it this form also. You can't put k equal to 1 through and put kt over, because it only applies to odd values. So this is the way you take care of it. Otherwise, you could simply leave that k odd here, whichever way. Okay, so let's do another example. So all these are discontinuous waveforms, and I'll talk about the discontinuity a little late. So you can see this is a 45-degree waveform. So ft is t over t by 2, right? And it is minus t over t by 2 on this side. So over a period, if you want, you can write it like this. I'm sorry, that's not right. So you have to write it, this is like over the whole period. Because when t is negative, it just takes negative values, comes up to here. So this swings between plus 1 and minus 1. This is also called a sawtooth waveform. So this has odd symmetry. So once again, it is of this form. So here, omega naught is 2 pi over t, whatever is the t. So here I just marked a general t. So this has the bk sine k omega naught t. This is an interesting problem. Let's see, do this. So of course bk is 1 over t, here 2, right? So again symmetry, right? So you have odd function. So bk, you can either use it over the whole duration or 2 over t and half the duration. So that's good enough. So we can write this over one duration ft sine k omega naught t dt, or again odd, so the product is even, over a common duration is 0 to t by 2. And for ft I'm going to, so if a picture is given like this, your first job is to sort of figure this out, the expression also, right? So I'm going to replace this by t over t by 2. So that becomes what? 4 over t squared, right? Integral 0 to t by 2 t sine k omega naught t dt. Okay, so here we just need to do it carefully, so I'll try to do it here. So you have to do the integration by parts. So one function, and let's take the first function multiplied by the, so this is dv, so what is v? Anybody? You have to find the integral of this. Huh?
Minus cosine over k.
Right, minus cos k limit 0 to t by 2 minus what? Integral? Right, so that this is the derivative of this is dt, so this is minus cos k omega naught over k omega naught dt, right? This is the right expression. As you said, this minus and minus will become plus, right? So I'm going to put a plus here, and there is no, that minus is gone. Okay, any of this you make mistake, it's so when you substitute, what happens? Top limit minus bottom limit. What's the value of the bottom limit? 0 because of this, luckily, right? So 4 over t squared t by 2 with the minus sign, right? Minus cos k omega naught t by 2. That's if minus 0, so divided by k omega 0. And let's come over here. What's the integral of cos? So what is it? Sine?
Sine k omega 0 t over k squared omega 0.
All right, very good. 0 to t by 2. So what's the value of the top limit? Omega 0 multiplied by t is 2 pi, divided by 2 is pi, sine k pi is
0.
And bottom limit? Sine zeros. So the whole thing is, so I hope you see this, right? So this is sine k pi minus sine 0. So both are 0, so that's gone. So you only have to worry about this term. So 1 t cancels, so you have minus 4 over t omega naught. I bring the omega naught from here. T and t cancels, 2 and 2 cancel. 2 and 4 you get 2. Cos omega naught t is 2 pi, so cos k pi. T omega naught is 2 pi.
There is also k.
Yeah, that's k, right. So minus 1 over pi k cos k pi. How much is cos k pi? We went through this.
Minus 5k.
K equal to 0, it is
1. Yeah.
1.
No.
I mean, remember it is bk, so we have to start from 1. K equal to 1, it is 1, you are right. K equal to 2,
No, if k equals to 1, it's minus.
I mean, K equal to 1, it is minus 1, right?
But there is a negative sign.
Oh yeah, there's a negative sign, so is that what you're saying? It's minus 1, but when you...
There's a minus 1. So K equal to 1, it is minus 1, minus plus. So k equal to 2, it is plus 1, then 3 minus 1, etc. So you can write like this. Right. So if you substitute all this, now we are almost done. We found out bk, so ft, which is t over t by 2, is 2 times bk. Bk is here. So bk is 2 over pi. So the first term is going to be, when k equal to 1, this is 1, right? So sine t. K equal to 2, it is minus so you can see how the pattern goes, plus, minus, plus, etc. There is no DC term, as you can see, right? Only odd terms. I'm just going to do several examples so that so that's good. Any questions on my simplification or anything?
Are we ever be asked to do like a function that's neither even or odd?
What is that?
Will we be asked to do a function?
I mean, in general, yes, because, for example, say, so this is perfectly possible, right? Look at here. This example. There is no symmetry, right? I mean, if this is the origin. So, that's a different issue. So then you have to be careful, then you shift. The issue is when you shift it, this also will become t plus t by 2. Essentially, you will end up with cosine and sine terms. And so in general, yes, you can have. So here what you do is, look at here. Here clearly you can see there is both cosine and sine terms. So you need to find out a naught, a case and b case. So in fact, you can try this example, right?
I have another question. For the simplification, why is the last term subtracted?
No, you mean here? So what I was trying to write was the next plus minus sine 5t over 5. Then what I meant to say was dots. A general term will be minus 1 to the power k plus 1 over k minus 1 over k. So that's what I meant to write anyway. And dot dot dot. Is that understood? No. See,
So when k is even,
when k is even, it is negative, right?
okay, yeah, I got it.
What happened to? Yeah, I mean, two negative, 4 negative, 6 negative, etc. Right? When k is even, because here when k is even, this is odd, so this will come about to be negative. You can from here also, right? When k is even, this is negative. When k is odd plus 1 is even, so that will be positive. So all the odd terms are positive and even terms are negative. So you just have to do it. The nature, if I put it this way, what happens? I don't know. You will have to do it. You can have the sawtooth waveform going the other way. Yeah, let me do some examples. An example which is not there in the notes. So how about this waveform? Let's say ft is t squared. What sort of symmetry do you see? Right. So if you want, you go home and do this from -1 to 1, but let me just do this for this. So what is the period here? 2 pi, so consequently omega naught is 1, right? 2 pi over t. So if it is even, what will be the expansion? A0 plus 2 sigma ak cos k omega naught t. Omega naught is 1, so it's pretty simple, right? And A naught we can compute directly. Sometimes that's easy. So A naught is what? 1 over 2 over t, 0 to t is 2 over 2 pi, right? That's the period. 0 to t by 2, which is pi. Ft dt, right? Ft dt. So Ft is simply t squared. So t squared. So that's t cubed by 3. So what do you get?
1 over 3 minus 0. No, pi squared over 2. Yeah.
Pi squared over 3. Okay, and ak is 2 over t, 0 to t by 2, ft cos k, omega naught is pi, omega naught is 1, cos t dt. So this is t squared. 2 over t is 2 pi, so that's 1 over pi, 0 to pi t squared cos kt dt. So you just have to do it integration by parts. So what is it? Ak is 1 over pi. So integration by part, we'll keep the first function as it. What is the integral of cos kt?
Minus sin kt is okay.
0 to pi minus integral 2t multiplied by minus sin k. All right, so the top limit is, I'm sorry, bottom limit is 0, and the top limit? Sin k pi, what do you get? Also 0, right? Because sin k pi, what is the issue? So this term goes to 0. Everybody sees this because the bottom limit because of this t is 0. Top limit is pi squared multiplied by sin k pi. Sin 0, sin pi, sin 2 pi, all zeros. So that's also 0. So then this problem reduces to minus minus plus. I pulled out a 2 here. 0 to pi. K is a constant, so that goes outside. There is a t here. Sin kt dt. That's what it simplifies to, if I didn't make any mistake. So we'll have to do this one more time. So this is 2 over pi k. Then same thing here. T. What's the integral of this? Cos kt over k 0 to pi minus integral. So this is dt. This is minus cos kt over k dt.
What is the negative cos? The integral.
Yeah, this is plus, right? That just putting the term right. I'm just still remembering this. All right. So what's the derivative of this? I mean, what's the integral of this? Just this term. Integral of this.
Sin kt will be by 6 squared.
Kt over k. So this becomes k squared. 0 to pi. So what do you get? Sin k pi is 0. Sin 0 is 0. So the whole point is that this whole thing goes to 0. So everything is here. Here, what is the bottom limit?
0.
Because when you put the 0 here, that goes. So a lot of simplification. So ultimately, only the top limit matters. So this is 2 over pi k squared cos k pi, right? What?
There's that pi which eliminates the t times cos, so it's pi times cos k pi.
Yeah, there is a pi here also. Substitute pi here. So pi and pi goes away. Is that what you said? So then when we do here, there should be a
There should be a negative sign in all of it.
or negative here.
Yeah. Yes, and that one should
I mean, but here ultimately it doesn't matter because this goes to 0. And here, because of this negative, the top limit, there will be a negative sign. Okay, so
And then after you integrate, you remove the minus sign.
okay, so there's a minus sign that this goes away. And this is cos k pi is what? Minus 1 to the power k again, right? Just k. So the answer here will turn out to be minus 1 to the power k over k squared times 2. Yeah, so the terms will alternate. And so you get, so the answer here is this t squared has a dc term pi squared by 3 minus plus minus is good, then 2 cos kt over k squared, right? So when k is 1, it is negative. So basically 1 squared minus 1 squared plus 1 over 2 squared, etc., etc. So notice when this is quadratic, you get the k squared terms. For the linear terms, if you recall, you get 1 over k terms. So you can also use this to do some summations. For example, what is the value of ft at t equal to 0? 0. So put a t equal to 0. So the left side is 0. The right side, this is 1, right? So you get, and then you, if you bring this term to the other side, you get this alternate 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared equal to pi squared by 3, which is a classic result also.
Can you get this like tan as a Fourier series? Tan as a Fourier series? Tangent to x.
So the issue is tan goes to infinity and plus infinity and minus infinity. So if you're talking about tan is certainly a periodic function, and so somewhere you will get constants which will blow up because the function does blow up, right? But otherwise, what symmetry does it have? Odd symmetry, right? sine over cos. So sine is odd, cos is even, so odd symmetry. So you can, symbolically you can write it in terms of sines, but the B case will explode. And also the integration won't be easy because there will be, in the original function there will be what? Sine over cos, right? So integrals involving 1 over cos is going to create issues. So let me do 2 examples which are, or at least one example which is a full wave, which is comes up in electrical engineering, full wave rectifier and half wave rectifier. And half wave rectifier is like this. In other words, if a waveform with plus and minus signs comes in, the absolute values are put out. So this waveform here will look like etc. And half wave rectifier is like this. So I'm going to apply this to a sine omega naught t waveform. So what is this waveform? Anybody? The input. What sort of symmetry you have? Odd, right. So this is, we'll write it like this. So what sort of symmetry does that have? So if you draw it, remember, it will look like this, right? Because originally the waveform was like this. This is whole period.
But it will be T when the period will change.
So let me draw the waveform. So what's the period now? Anybody? Right. So the new period is T1. So for this waveform, omega naught will be 2 pi over whatever is the period, which will be T by 2. So I'll simply call it omega naught. So
Professor, what did you do with T by 2?
I'm saying here omega naught is some 2 pi over T, right? So the period is, so for the original waveform the period is T. And let me make a special case. Let's say this original waveform has period of 2 pi, which is just a sine T. So we can do this special case. So here the period is 2 pi, and in that case here what will be the period? Pi. And omega naught will be 2 pi over the period. So omega naught is 2. So this waveform has what kind of symmetry? Even. So this you can write it as, this is our Ft. So Ft can be written as A naught plus 2 sigma AK cos 2 kt, right? Because omega naught is 2. And A naught itself is what? A naught is the area under any, so it's going to be 1 over the period, that's 1 over pi, 0 to pi, this waveform. What is this waveform? What do you see here? This is just a sine t, right? See, when the waveform is positive, of course, absolute value of sine t is sine t. So sine t dt. And the derivative, the integral of sine t? So what do you get? 2 over, right?
2 over.
Because alright, so that makes sense because there will be some residual DC value. Now AK is the one. So for AK is 2 over T. So I'll write it as T1. Whatever is the T1, we'll come to that. Ft cos K omega naught T. Remember, omega naught is 2, so 2 kt dt. So T1 is pi, so 2 over pi, 0 to pi. Ft is what? Ft in 0 to pi, look at here, Ft is just sine t. So this is sine t cos 2 kt dt. So how do you do this integration? You have to use sine A plus B is what? Sine A
Cosine B plus
So look here, we have sine A. Either way you can read it. If you want to put this as the first one, you can read this as cos 2 t sine t. So you can see if you subtract this from this, so which is what, so this is your cos A sine B, not cos B. Cos A sine B. So this term can be written as sine 2k plus 1 t minus sine 2k minus 1 over 2. So I'm going to put that here. So 2 cancels, 1 over pi, 0 to pi, sine 2k plus 1 t dt minus sine 2k minus 1 t over dt. So this is 1 over pi minus cos 2k plus 1 t over 2k plus 1 minus 2k minus 1 t over 2k minus 1. We can do a little bit simplification here. So top limit minus bottom limit. So the bottom limit will come first because of the minus sign. So 1 over pi 1 minus cos 2k plus 1 pi over 2k plus 1. So again same thing here, right? 1 minus cos so you can look at the thinking now. So what is this? We went through this, right? Cos k pi is minus 1 to the power k. So how do you, because k equal to 0 you get 1, k equal to 1 you get minus 1, etc. So cos 2k plus 1 pi will be minus 1 to the power 2k plus 1. So you see this, because when you raise something to minus 1, if you add plus 2 or minus 2, it doesn't matter. So both of them, you can write this as this, or you can write this as that. So this, what is it, AK,
This value will always be -1, right? The value will always be -1.
the value will be plus 1 and minus 1, right?
-1 for any. It's always off. The power is always off for any case.
2k plus 1 is always, what did you say?
It's always off.
Negative 1, right?
Yeah, it's always negative. So we can remove this and do 2 over 2k plus 1 plus 2 over 2k minus 1.
So if this is negative 1, if this is, since this will be always odd, so minus 1, this will be 2 over 2k plus 1, 2 over 2k minus 1. And then so I only have k here, why 2k, let me see, k plus 1. I mean, there's nothing wrong with what we did, so this will turn out to be but let me see why this is slightly different from what I have here. Where is it?
So it would be plus sine minus
Here?
The formula you gave is up there. The table.
This one?
Yeah.
Yeah, but so look, if you add these two, you'll get sine A cos B. I wrote it here cos A sine B. If you want cos A sine B, you need to subtract this expression from this expression, because this goes away, right? So that's correct. Now the issue is with the 2. Hang on, let me see where the mistake is. So I will have to see, I have here as simply cos, I put everything in omega naught, so when I do it in my notes, I'll double check, let's not waste time now. This comes out to be k plus 1. If that is the case, then we will have to go through different cases here. But the way we have done, you don't need all of this, that's right. So what I had was sine omega naught t but then this must be 2 omega naught t, right? Because if the original expression is sine omega naught t, say this is sine omega naught t. Sine omega naught t goes to 0 at pi, and then the absolute value again stops. So this new omega naught will be 2 omega naught. Omega naught prime would be 2 pi over t by 2, but t is 2 pi over omega naught divided by 2, so that's multiplied by, so the whole thing will come out to be 2 omega naught. So this is right. If that's the case, that will be the A case. So the whole point was to find out the A case and B case.
Professor, for the finding AK, are you using the formula for the even function?
Right.
Yeah, so I think the upper limit for the integral should be pi over 2. Because that's half the period, right?
No, because the period was 2 pi.
No, look at here. For this function, period is not 2 pi, period is pi. Don't you see it, right? The problem is given, this is the period, right? So AK is, AK we have couple of formulas, hang on. AK, remember it's 1 over t integral 0 to t ft cos k.
In this case, we should just remove the t.
This is the general formula for ft, right? So if there is no symmetry, it will be just this expression. In general, if there is symmetry, we went through this, right? If there is symmetry, you can always write this as this way. Then we can write it as 2 over t 0 to t by 2 ft cos k omega naught t dt. So here it is true, there is symmetry. But you are also right. I could have done half, but I chose to do. So remember, this can be always done. You can either do this. Both are correct, I am saying. Right. So I just happen to use this expression. But you are right. I could have also. What you are trying to say is what? I could have just integrated up to here. Is that what you are trying to say?
Yeah, because I saw that too in the coding edition.
Look at AK, you're integrating from 0 to pi, not pi by 2. So you're using the formula for half the period that you're integrating over.
Why is it half the period? Look
The
at
next one, on the next board, AK is 2 by t1, but you're doing 0 to 2, 0 to t1 to 0 by t1 by 2. No. So you're integrating from 0 to pi instead of 0 by 0.
no, that's okay. So this will term 1. That's all. Yeah. But both are right. So you can either integrate from 0 to pi, or you can also integrate over half the region. Because of this symmetry, AK can be written as, so this should be what? 1, okay. At least let's get the formulas right. So this is fine, but just because she said this also can be written as 2 over pi integral 0 to Is this what you're trying to say? Both expressions are right.
Yes.
So I happen to use this expression. In the homework, if you do this, you should come up with the same answer. So, especially because there is symmetry here. Now, let's take the other case where there is no symmetry, then you may not be able to use this, I think. So how about this problem? Suppose this goes to a half rectifier, let's say sine omega naught t. What comes out is output is ft. So we know this waveform is like this, right? And the output waveform will be now like this, then 0, like this, etc. So what symmetry do you see here? All right, right. So this ft will be a naught plus 2 sigma a naught to ak you can write, so you can a naught is definitely non-zero because you can see there is a DC value, right? So a naught, it is enough to do it over a period. So you can say the period I'm going to think of from here to here. So a naught will be integral 0 to whatever is this point. So if I keep it as so remember, for this omega naught there is a period. So you have to see all this stuff, right? This omega naught corresponds to a period of t. That t will be this. So physically this point is t by 2. That's the period of this. So this is T1, the new waveform. I'm sorry, the period is still the same, right? This much. So period doesn't change because that's when it repeats. But this point is of course T by 2. So A naught goes from T by 2 ft dt. Ft is what? Sine, right? So ft is sine omega naught t dt. 0 to T by 2. So minus cos omega naught t over omega naught 0. So you just substitute and simplify, etc. So omega naught t is 2 pi over t, or omega naught t is always, remember this, 2 pi. So when you substitute here, omega naught t by 2 will be pi. So cos pi is minus 1. So this is minus minus goes away. 1 over omega naught, which is, so that's the A naught. Then you need to find out A case and B case here because there is no symmetry. So AK will be, so we just, because we have no symmetry, we just need to stick to this expression. Previously the 2 etc. came when this had even symmetry or odd symmetry, right? So AK will be 1 over T but if you remember, if you integrate over up to T, it is all 0. So it's enough to integrate up to T by 2 for a different reason, because the function is 0. Then multiplied by the function, which is sine omega naught T, multiplied by sine. So what is the period of this waveform? The period of this waveform? No, also T, right. So unlike the full rectifier, here period stays the same. And so omega naught will be the same. So this will be simply k omega naught T dt.
We can assume that it's, like in the first case, you can assume it's.
It is what?
We can assume that the period is still T.
Yeah, it's not the smallest.
Period is not assumed, period happens to be T.
No, for Fourier.
Yeah, for the first.
That's not the smallest T. Then here you can assume the period is this much, right?
Yeah, but we figure the same as well.
Yeah, but usually the T is referring to the smallest one. There may be some contradiction. I am not 100% sure. I see what you are saying. But usually the capital T is the smallest value for which you have this relation true. If T is, I mean, this is true for any T, but what is the smallest value of capital T? So here again, AK will turn out to be, as we did before. So what was that? Sine k plus 1 omega naught t. Yeah, here it may be slightly different. Minus sine divided by 2. So I'm going to take the 2 outside. Then the integral of sine. So that's minus cos k plus 1 omega naught t over k plus 1 omega naught. There's a t here, so then I'll only pull out half out. This from 0 to t by 2 minus plus cos k. This t is coming from here, and upper limit 0 to t by 2. So you just do it like this. So to complete a few more lines, so omega naught t is 2 pi. So we can pull out 4 pi outside. Same thing here. So this is omega naught t by 2, right? So this is omega naught t by 2. Omega naught, this is pi. So this is k plus 1 pi, right? Minus cos k plus 1 pi divided by k plus 1 plus so you need to simplify like this, and at this point, what is it now? So k plus 1 okay, so this much is fine. Now look here. If I add here 2 or subtract, because minus 1 squared is plus 1. So notice that I can also put this as plus 1. It doesn't matter. Not here, but there. Then that minus 1 squared goes outside. Then the numerator is minus k plus 1 here when this goes there, and here minus k.
Shouldn't there be a 2 somewhere?
2?
Oh, sorry, no.
2 cancelled somewhere. I mean, this 2 and this 2 gave us 4. This is plus, right? So that's what it will come. I mean, if it is plus here, then so I pull out minus 1 to the power k plus 1 outside. There's a minus 1 here plus here. So this will go here minus k plus 1, then k plus 1. So k cancels, and you get 2, 2 and 2 cancels. So that's a constant for A case. Similarly, you have to find a B case. For example, so I'll do that. BK will be what? 1 over T. Again, you have to go through this, right? Integral 0 to T, but the function only has value up to T by 2, so it's enough to integrate up to T by 2. And during that function, the function is sine omega naught T multiplied by sine k omega naught T dt. Now, anybody remember how do you simplify this in terms of 2 terms? Sin A sin B is what? How do you get sin A sin B? Alright, so let me consider this to be A, this to be B. So what somebody said cosine A minus B? Cosine? Very good. Over 2. Right. So it will come out to be this one. So this is 1 over 2t sine k minus 1 omega naught t over k minus 1. Same way, omega naught minus sine zero to t by 2. So we have ak there. So bk will be, so the bottom limit is 0. What about the top limit? Anyone? So what is the bk value? 1 over 2t. Look at the terms. Sine k minus 1. Omega naught t is 2 pi. By 2 is pi divided by minus 0. Sine 0 is 0. K minus 1 omega naught. What is the value of this? Sine multiples of 0. Also 0, right? And same thing here, sine k plus 1 pi divided by. So interestingly, the bks is 0, but there is no symmetry because of, if you remember, a0. A0 was not 0. A0 was whatever. What was A0 was a number, so because of the A0, but bks happens to be 0 here. So only, once again, A0 and the bk terms.
So is it true in general that A0 is only non-zero, like the average is not 0?
Right, exactly.
And then what's the meaning of A0 again?
Hang on. So you can see it from here. If you have a signal, what I'm doing is just taking the average.
Right.
So what the statement what you said is right. A0 is the average value. Now what your question is, what is B0? B0 is always 0. Remember, we went through this earlier. So the question is, what is AKs and BKs? AKs and BKs are the amplitudes of the frequency k omega naught.
So like, sorry, the sawtooth we did earlier, just from looking at it, you know A0 is 0.
Actually, you know more. What about the AKs? Just by looking at it.
They're all saw, I don't know.
No. What sort of symmetry does have this sawtooth?
Odd.
So what will be the AKs?
Zeros.
Remember, we went through this. If waveform has odd symmetry, all the AKs will be 0,
Right.
including A0, obviously. So only BKs are non-zero. So you don't even have to start computing AKs, I'm saying. By looking at it, you know it's only BKs for odd symmetry.
Well, it's possible to have odd symmetry and A0 be non-zero? No?
See, odd symmetry would means it's always something like this, right? FT is. So let me answer your question properly through this. Odd symmetry means what? F of minus t is f of t. F of minus t is minus ft, right? This is odd symmetry. What is the value of A0 or any AK? Anybody? AK will be 1 over t minus t by 2 to t by 2. So you can answer this in one shot. So put k equal to 0, you get A0, right? But let's say this has got odd symmetry. This has got even symmetry. So the product is, what is this is odd by definition, right? This is even.
Right.
So odd multiplied by even is integrated over a symmetric region. Look at here, integrated over a symmetric region, what do you get? Here.
0.
Right. So all the AKs are 0.
Yes.
A0 is a special case of this. A0 is a special case of this, right?
Yes.
Or you can directly look at the picture. What is A0? The average value over a period.
It's 0.
0. So to answer your question earlier, you said, can an odd function have an A0 which is non-zero? The answer is right here, no. So why are you thinking it is possible, right?
Because I'm imagining like a sawtooth shifted upwards so that...
Then it will lose the symmetry, I think. So let me draw what you are saying. So we are sort of done with this example. So let me answer some general questions. I do have a little bit of, if you shift a sawtooth, it will look like this.
Oh yeah, it does lose its symmetry. My bad. Sorry.
So if you shift a sawtooth, it will look like this.
Yeah,
This doesn't have any symmetry.
exactly.
Of course, you can shift it down and make symmetries, right? So a couple of things what I have not mentioned, let me mention here. So if you have a function, the whole point is this, so ft is, I have some of this proof of what I'm saying here in my book, in my notes, so you can read it, but I'll give you a summary of two results. That's good. Has a representation of this form. So that's what we have been, so what does this mean? What this means is if you look at the partial sum, so let me make it more precise. So there is a decent proof of this in my notes. So instead of writing minus infinity to infinity, consider this partial sum. So this is, I use this notation Fn. So Fourier's result is that as n goes to, n becomes larger and larger, this will become indistinguishable by this, from this. Fnt will tend to ft. That's what, yesterday when I wrote like this is what I meant. So you can ask what happens at points of discontinuity. So we need to, so let me look at this function. This is continuous everywhere, whereas a function like this has discontinuity. Because from here it jumps to this. So the complete theorem is the partial sum, this is the, so if ft is periodic, it has a representation of this form. What that really means is, if you take the partial sum from minus n to n, including 2n plus 1 terms, this partial term tends to, and if you superimpose the partial sum on top of the, so it will hug the original function as n becomes large. That's what the meaning of the thing. So what happens at the points of discontinuity? Obviously, discontinuity, the value is, you have several values. The point, it has no single value. It could be this, you can define it as this, or the middle value, or any other value, depending on the definition of the function. So there the Fourier has proved that this partial sum goes to, so if there is a point of discontinuity at t naught, you can approach the function from the left side. That value is known as t naught minus. So what is ft naught minus? It's the limiting value of f of t naught minus epsilon as epsilon goes to 0. As you approach the function from here, As you approach the function from right, you get another value. That's what we mean by discontinuity. So I'll write it like this. T naught plus is limit epsilon goes to 0, f of T naught plus epsilon. So at if you have a discontinuity, what do you mean by discontinuity? That means these two values are not the same. So you have a sawtooth function is discontinuous, right? Sawtooth. This is a discontinuous function. At the discontinuity, if you come from the left, you get +1. You come from the right, you get -1. These two values are not the same. So what happens at the points of discontinuity? This partial sum will converge to its average value of the discontinuity. That's Fourier's complete theorem. T naught is a point of discontinuity. So if there is no discontinuity, the function will go to the, so a point like here, if you come from the left or right, the value is the same as the value of the function. There this partial sum will converge to the actual value. So let me draw the Fourier series representation of a discontinuous function. So a discontinuous, it's right here. So for a discontinuous function like this, if you compute the Fourier series, partial sum will come. It will converge to this value. On top of that, there will be some ringing here at the discontinuities. Overshoot and undershoot. So the first result is at a point of discontinuity, two things happens. Number one is this: at a point of discontinuity, the partial sum converges to the average value, and the second one is at those points there is also an overshoot by roughly about 9% and an undershoot also by 9%. That is something you cannot avoid by taking more and more terms. Even if you keep adding more and more terms, the overshoot and undershoot will persist.
When you say point, you mean a point on the x-axis or the y-axis? But when you say point, you mean like a point on the relative to the x-axis? Because in that case, like we overshoot, undershoot, or in the same?
No, I mean, a point T naught is here. There is a discontinuity here, right?
Yeah.
At the discontinuity, there will be an overshoot on these terms. If you compute those terms,
For example, in this case, at point, or like at first.
here there will be a discontinuity here. There is a discontinuity here. There is a discontinuity.
So will it be half?
Right. The convergence will be to the middle value, whatever it is. So the convergence, if this is +1 and -1, the function, if you compute this thing, that will go to 0. But there will be, but to the immediate to the left and right, there will be overshoots and undershoots. This is known as the Gibbs phenomenon.
It passes through the.
Yes, through the average value.